This is fundamental problem 31 from chapter 12. If the motorcycle has a deceleration of negative 0.001 s, and this is the tangential component of the acceleration, and its speed at position A is 25 meters per second, determine the magnitude of its acceleration when it passes point B, so the magnitude of the acceleration at point B. Point B is shown here, and they're showing us that this is the tangential direction. So you could also tell that that's the tangential direction because we started at point A. So if we go from A to B, we're going in this direction, which is the tangential direction, and the normal direction points in towards the center of the circle. And the radius is 300 meters. If the car is going in a circle, the radius of the circle is the radius of curvature. So we don't have to use this formula to figure out the radius of curvature because it's simply 300 meters. And I want to find the magnitude of the acceleration at point B, so let me take a look at what I have. I need v squared, but this is at point B, and all I have is the velocity at A. So I need the velocity at point B. I have the radius of curvature, so that's good. And this is the tangential component of the acceleration. So I need this at point B. Well, I think I can figure that out quite easily because they also show you on the diagram here, you're measuring S, and S is equal to 0 at point A. So when I'm at point B, the S that I would have in this formula here would be the distance from A to B. So that's a quarter of the circle. And I know the radius is 300 meters. So let's just do that now. At B, S is equal to a quarter of the circumference. The circumference is 2 pi r, so that's 1/4 of 2 pi r is 300 meters. And that is 471 meters. You could also get that from the arc length formula, and this may remind you of what you did in Physics 261. Okay, so we have S at point B, and I need the speed at point B, and it looks like once I have that, I'll be good. Okay, so notice that here, they give you the tangential component of the acceleration as a function of position. That should remind you of equation 12-3, but we're going to use, for normal and tangential components, equation 12-19. So I have the tangential component of the acceleration times ds is equal to v dv. I want to start off at point A because I know the velocity at point A, so that's going to be my lower limit of integration, and my upper limit of integration is vb, which is what I'm looking for. My lower limit of integration here is the value of s when we're at point A, so that agrees with our lower limit here, and from the diagram we saw that s is equal to 0 there. My upper limit of integration is s when I am at point B, which is 471. It might be a good idea in general just to leave your upper limit of integration as v and over here as s, and then you can plug in the values for b later. But I think we're going to be fine doing it like this because it looks like all we need is the velocity at point B. So I can go ahead and plug in 471 for the upper limit of integration there, and we'll see what we get. So I have to take the tangential component of the acceleration and put that in. So we're going from 0 to 471 meters, and I have negative 0.001 s integrated with respect to s. That looks like it will be easy to integrate, as will the other side. I'm going to leave this just as VA for now and put in the 25 meters per second later. Okay, so when I integrate v dv, we have seen this many times before. We get 1/2 v squared. We're going from, let's put in the 25 now, to vb, and this is going to be 1/2 of vb squared minus 25 squared. Okay, and then when we integrate with respect to s, we can pull the negative 0.001 outside the integral. When I integrate s with respect to s, I get 1/2 s squared. And if you'll allow me to plug in the limits of integration as I do this, so I don't have to write it over again, we get 1/2 s squared. So I put in the 471. I'm going to leave the units out because I didn't put them in over there. And when I plug in the lower limit of integration, that's just 0. So it looks like now we can solve for VB. So let's multiply both sides by 2, and we have negative 0.001 times 471 squared. So we got rid of the 1/2, and then we can bring the 25 over to the other side, so that, well, the 25 squared. And then if we take the square root, we get VB, and we better hope that 25 squared is, greater than what I have there. Otherwise, we're going to be getting something imaginary, but I think it should all work out. You can go ahead and plug that into your calculator, and you should get 20.08. In this problem, well, the velocity was given to us in meters per second, so this would be meters per second. That wasn't what we were looking for, though. We were looking for the magnitude of the acceleration, but I should have everything I need now. So we're using this formula here first to say the acceleration at point B, v dot, what is, well, I think we still need to find that. So it would just be what I have here when s is equal to 471. So negative 0.001 times 471 in the tangential direction plus v squared. V is, 20.08 squared divided by the radius of curvature, which is 300. Okay, and that's in the normal direction. So let's go ahead. You can put that into your calculator. You should get negative 0.471 in the tangential direction plus 1.344 in the normal direction. And finally, to find the magnitude of the acceleration, we have 0.471. If you want to put the negative sign in there, you can. It's not going to change anything. 1.344 squared. Then take the square root, and we get 1.424 meters per second squared for the magnitude of the acceleration. And that concludes problem 31.